welcome back to this matter this matters eCHT research seminar. And for the first talk, today we will have Jeremy Hahn from University of Cambridge. And he will tell us about making the motivic spectral sequence for TC of MU explicit.
Yeah, so thank you very much for the opportunity to speak. And I'm going to talk about a piece of some kind of sprawling thing that in writing with Sanath, Devalapurkar, Arpan Raksit, and Alan Yuan. And I guess the goal of this talk is going to be to say something about how one might compute or understand the homotopy groups of the algebraic K-theory of MU. And maybe a kind of question to highlight. There could be many interesting questions to ask about this object, but one of them might be, what is the Hurewitz image? What elements in the homotopy groups of spheres are detected in the algebraic K-theory of MU? I think there's a potential, for example, to see a lot of Greek letter elements in there. And yet, I think the algebraic K-theory of MU will be in many ways simpler than the homotopy groups of spheres. And so it's a potentially more approachable object that might nonetheless see a large amount of the homotopy groups of spheres. So in order to compute this sort of thing, we can use the Dundas-Goodwillie-McCarthy theorem. There's a fiber square relating the K-theory of MU, the TC of MU, the K-theory of the integers, and TC of the integers. And the bottom row is very well studied. Lots of things are understood about it, not everything, but in particular, these only see height 1 information by redshift. So if you're interested, for example, in detecting interesting elements in the homotopy groups of spheres, you may not have to worry so much about the bottom of this fiber square, because that's only ever going to interact with height 1 information anyway. And so what I will try to focus on is what can be said about the homotopy groups of TC of MU and the Hurewitz image of the sphere in those groups. So one could wonder—
Can I ask a question?
Yeah.
Well, doesn't the DGM theorem require something about a nilpotent kernel of the map?
Yeah, so it requires you to have a nilpotent kernel on pi 0 if you have a map of connective rings. And so this is an isomorphism.
Ah, only on pi 0.
Yeah.
Okay. All right. Thank you.
Okay, so I'm immediately switching to TC, which is what I'm really interested in. And you could ask, whether it's at all reasonable to expect to be able to compute pi star of TC of MU. And the way I want to compute it is via a motivic spectral sequence. Converging to the homotopy groups of TC of MU. And it's some motivic spectral sequence that's being explored in this joint work and building on work with Raksit and Wilson. And what I would like to do is today get as far as possible in sort of describing the E1 page of this spectral sequence. And I want to describe it as a DGA, or in other words, the Kovar complex associated to an explicit Hopf algebroid. So in theory, if I get through all that today, there will be a completely algebraic way of computing the E2 page. And you could ask sort of how far is the E2 page from the answer, and I will make a conjecture, which is that the motivic spectral sequence for TC star of mu collapses at the E2 page. So I do believe that the TC of mu is substantially simpler than the homotopy groups of spheres, and that as far as I know, this conjecture could be true, and it's the computation of the homotopy group of TC of mu can be essentially completely algebraized, though that doesn't mean the algebra is easy. I want to contrast this with what happens for the sphere. So the motivic spectral sequence for, say, TC star of the sphere, P completed, contains a summand that is isomorphic to the Adams-Novikov spectral sequence. And that, of course, does not degenerate at the E2 page. There are many differentials in the Adams-Novikov spectral sequence. So as far as I know, the motivic spectral sequence for TC of mu is substantially simpler. For example, it has much better vanishing regions and vanishing curves than the Adams-Novikov spectral sequence. Now, I don't know how seriously you should take the conjecture that it collapses at the E2 page, but I think it might be somewhat reasonable. And in any case, making that kind of conjecture may encourage some people, I hope, to engage with the algebra of this E1 page I'm going to describe, and maybe make some explicit computations of TC of mu. So before getting into the E1 page, maybe I should just very briefly remind everyone about what TC is so we can see how to calculate it. So what is TC? So if A is an E infinity ring, I can compute THH of A, and it's the colimit of the diagram from circle, thought of as a category or a groupoid, to E infinity rings, which is constant. So it's a kind of boring functor, constant at A. And so because one takes the colimit of this constant diagram, there's an action of the circle which allows us to form invariants like I could take THH of A and take the homotopy fixed points for the circle action, or I could take THH of A, take CP, where I'm thinking of CP as sitting inside of the circle. So because the circle X, CPX, and this will have a residual leftover action of S1 mod CP, which is just another copy of S1 written differently. So there are some invariants one can extract out of THH. And from just these invariants, if A is connective, Nikolaus Schulze defined TC. So Nikolaus and Schulze proved that, say, after completion at some fixed prime P, you can describe TC of A, again, up to P completion, as an equalizer of two maps, THH of A, HS1, to THH of A, to CP, HS1, where that second HS1 is for the residuals S1 mod CP action. And these two maps are often called CAN and phi P HS1. So, all right, that's a formula. Now, in the special case of MU, there's a beautiful theorem by Nielsen and Rognus, which says that the map IP HS1 is, again, up to P completion in equivalence. And this is when A is MU, very specific to MU, this case of interest. So we're trying to compute an equalizer of two maps between isomorphic rings where one of the maps is the isomorphism. So the upshot of all that is that to compute TC star of mu, one must accomplish two things. First, we have to compute the homotopy groups of the circle fixed points. And then for each prime P, understand the endomorphism pi star of, I guess we can go by the CAN map, and then the inverse of this equivalence, and this will be on pi star of THH of MU HS1 P completed. Okay, so there's a basic object one has to compute, which is the homotopy groups of these fixed points. And then thanks to this wonderful theorem, there's the only other data involved in computing TC is for every prime and endomorphism of these homotopy fixed points. So my main goal today is to sort of describe how one might compute A, and then if there's time, I will discuss how to compute these endomorphisms. So first, let's discuss A. How would you compute the homotopy groups of these fixed points? Okay, so naively, the first thing you would do is compute the homotopy groups of THH of MU, and then you would run a circle homotopy fixed point spectral sequence. So here's a theorem, which is non-equivariant, and it's due to Blumberg, Cohen, and Schlick rule. And it says that THH of MU is MU adjoin SU. Okay, so non-equivariantly, THH of MU is just the MU homology of SU. And roughly speaking, the way one proves this theorem is that MU is the Thom spectrum of BU. And the other important fact is that loops on SU is BU. So these two facts combine, thanks to this work of BCS, to prove this fairly simple description of THH of MU. And so in particular, the homotopy groups of THH of MU are the MU homology of SU, and that's just an exterior algebra on a bunch of classes that are in some places in the literature denoted by lambda I prime. But it's just an exterior MU star algebra. on odd degree classes. Okay, so that's really not so bad. And then the only remaining thing to worry about is a S1 homotopy fixed point spectral sequence. So there is a homotopy fixed point spectral sequence, which will start with this exterior algebra on these classes. And then you will join power series generator, and it will converge to this object of interest. Now, because these generators, the lambda I prime, are in odd degrees, there's room for a lot of differentials to potentially happen in this homotopy fixed point spectral sequence. And so there's a wonderful paper by Raksit who writes down a formula for the first differential, the D2 differential. But the answer turns out to be quite complicated, at least from my point of view. Even when you understand this D2 differential, there are certainly many longer differentials in this homotopy fixed point spectral sequence. So I'm not sure how feasible it is to directly approach this homotopy fixed point spectral sequence. Maybe from this point of view, it's not so clear how you would figure out any kind of formula for the longer differentials, and things will get very complicated very quickly. So I'm going to present a different approach than running a homotopy fixed point spectral sequence. So we'll call this the motivic approach. And there's reasons that it's called the motivic approach, but for the purposes of this talk, I just want to be very concrete and computational. So I'm just going to tell you how to construct the motivic spectral sequence in a kind of straightforward way and not really describe why it's called the motivic spectral sequence or anything fancy like that. So it's actually a quite concrete idea in this example. So we're just going to note that there is a map THH of mu to mu, where here we have this interesting and necessarily highly non-trivial circle action, because if the circle action were trivial, we wouldn't have seen all these interesting D2 differentials in Raksit work. But here we just have a trivial action. And it is completely formal to construct this map from the description of THH of mu as a co-limit of the constant diagram. So this is a simple enough map. And so we can use it to do descent. We write THH of mu as the limit of a certain diagram, mu tensor over THH of mu, and we just keep going. And so I'm just writing the Adams descent, which you can do whenever you have a map of rings. But in this case, maybe an interesting thing to note is that taking HS1 commutes with limits, because homotopy fixed points is itself a limit. And so we can take the limit of this totalization for the circle action and get some kind of totalization that will compute the homotopy fixed points of THH of mu. So before worrying too much about homotopy fixed points, let's just think for a moment about what this descent object is doing non-equivariantly. So non-equivariantly, we know that mu tensor over THH of mu and mu is just the same thing as mu tensor mu adjoin SU, mu, which is the bar construction. So we get mu homology of BSU. Right? I mean, if you really want to think about this in a fancy way, the mu homology of BSU, by this symbol, we just mean I take mu and I tensor it with the suspension spectrum of the fourth infinite loop space of Ku. That's what BSU is by Bott periodicity. Okay. So what we're doing here in this descent is we're writing mu adjoin SU as a limit of mu adjoin BSU, mu adjoin BSU squared, etc. So this is just mu tensored with the cobar complex for BSU. So if I take cobar of BSU, I get SU, because bar of SU is BSU, and this bar cobar duality. Okay, so I hope that's not too bad. But now I want to think about equivariantly. What happens so as an S1 equivariant spectrum, mu tensor over THH of mu turns out to be not too hard to describe. Again, using this kind of Tom spectrum description. Same techniques. So the same kinds of things that went into the identification of mu homology of SU. And when you're really careful about tracking the equivariance, what you see is that you get the mu homology of B lambda BU. I'm using that lambda symbol to say something about the equivariance. So if I want to be very concrete, that's the mu tensor sigma infinity plus loops infinity suspension of 2 plus lambda of Ku. Okay, and here lambda is the standard representation of S1 on the complex numbers. And so you can see that non-equivariantly that matches up with this sigma 4 Ku we had earlier, but now when one's careful about the equivariance, you really see 2 plus lambda. Okay, but lowercase ku is a complex-oriented spectrum, where it's complex-orientable, right? So because ku is complex-orientable, mu tensor sigma infinity plus loops infinity sigma 2 plus lambda ku is the same as if I just put a 4 here, even equivariantly, right? That's just because ku lambda suspended is the same as KU2 suspended, even equivariantly, because KU is complex orientable. So you have a Thom isomorphism for a complex representation. So in other words, if I look at mu tensor over THH of mu, this has trivializable circle action. This is a point that was very much emphasized to me by Mike Hopkins. This is pretty amazing. The fact that the circle action here has a trivialization means, for example, that any kind of circle fixed points spectral sequence will degenerate, and it will degenerate immediately on the E2 page. And in fact, if you're careful about the trivialization, you can really name elements in the homotopy fixed points of this thing. So if I look at this totalization, mu tensor over THH of mu. Here, this has trivializable circle action. It's got trivial circle action. We mapped from THH of mu to mu as the trivial circle action. And so does this, and so does this, et cetera, et cetera. So every stage in this tower has a completely trivial circle action, but the limit of the tower, or the limit of the cosimplicial object, has an extremely interesting non-trivial circle action. So what's happening here is that these trivializations cannot be made compatible with the cosimplicial structure maps. Right. We've somehow broken this thing into objects that have trivial circle actions, but the reassembling process is what will introduce the non-trivial circle action. Okay, but one can study pretty explicitly how these trivializations change under the Hopf algebroid maps here. And when one does that, quickly encounter some formulas from Ravenel's Green Book, and known formulas such as the formula for eta r of t, where t is the complex orientation of mu and things like that. So maybe I can describe to you how does this Hopf algebroid look explicitly. Could I track everything well enough to actually write down an E1 page that can be fed into a computer and perhaps turned into an E2 page for the homotopy fixed points of THH of mu?
Could I ask a quick question?
Yeah.
When you say they can't be made compatible with the cosimplicial structure maps, can they be made compatible one at a time, but not like all of them at once?
Yes. So you can, like, for example, if you look at just the first two elements in the cosimplicial structure map, you can make one of the two of the left or right unit be triv of something, but not both simultaneously.
Not the other. Thanks.
Right. So, okay. So let's see how I can describe this. So, all right. So first, maybe we've learned that the best way to think about Hopf algebroids, or at least a way to describe Hopf algebroids that is in principle digestible, is to ask what is the stack that it presents. That stack, remembering the E2 page we are interested in. So for example, the kinds of stacks we might see in the Adams-Novikov spectral sequence would be MFG, and this is going to be some other stack that probably has something to do with formal groups. So first, non-equivariantly, just as a warm-up. We're looking at a stack associated to this Hopf algebroid. We have mu star, and then we have mu star BSU, and then we have mu star BSU squared. And here the cosimplicial maps are not particularly terrifying because it's just the cobar of BSU becoming SU. But if we're trying to describe this algebra geometrically, this is some category, some groupoid, where the objects are represented by mu star. So the objects are a formal group with the coordinate. That's what a map from mu star to some ring classifies, a formal group with a coordinate, in other words, a formal group law. And the morphisms here are classified by the mu homology of BSU. So there's a result of Ando, Hopkins, Strickland, which tells on what the mu homology of BSU classifies. And what it classifies is, again, you have a map from mu star, so you have a formal group with coordinate, and you have a GM valued symmetric 2 cocycle. This is what Ando, Hopkins, Strickland tell you you get. And so what is that? That's a function from the formal group across itself to GM, which is symmetric in the two variables and satisfies some kind of relation that's called the 2 cocycle condition. So you can read about the exact definition of a GM valued symmetric 2 cocycle in their work. But here, that's not what the objects are, that's what the morphisms are, which might be a little bit strange to get one's head around. But one way of saying what's going on is that this stack classifies formal groups G hat with the coordinate and a PGM valued symmetric 2 cocycle that is locally trivial. That's just a formal thing about how one might define a BGM valued symmetric 2 cocycle. The morphisms are giving you a GM valued symmetric 2 cocycle. So somehow there's a map from the formal group cross itself to BGM. So there's some kind of canonical line bundle from G hat cross G hat to BGM. But locally, that's going to be a trivializable line bundle. But globally, somehow, you're going to see a GM valued symmetric 2 cocycle controlling things. All right. I want to just remark, this is all a little bit elaborate, but it makes the S1 equivariance story clearer. What is a coordinate on G hat algebra geometrically? So algebraically, it's some identification it's something like in an element of xk adjoin x, an identification of that module with the trivial k adjoin x module. But geometrically, one way of thinking about it that I learned from Arpon is coordinate is the data of a trivialization of a certain line bundle. The line bundle of functions that vanish at the origin on G hat. So you have your G hat, you have your BGM. This is the line bundle of functions that vanish at the origin. In other words, x, k brackets brackets x, not an arbitrary power series. It has to vanish when you plug in 0. And we have the trivial bundle, and we have a trivialization. Okay. So a very fancy or algebro-geometric way of describing the stack computing THH of MU without any circle action. It classifies a G hat, a trivialization of this canonical line bundle, which is, in other words, a coordinate. And then we have a locally trivial symmetric 2 cocycle. And that's some kind of description. So what about S1 equivariant? So we're going to have now mu star adjoin T. And here we'll have mu star PSU adjoin T. And then mu star PSU cross PSU adjoin T. So what am I doing here? I am taking homotopy fixed points everywhere in that cosimplicial object. And I told you that level-wise in that cosimplicial object, everything has trivial circle action. So because everything is level-wise trivial circle action, when I take homotopy fixed points, I'm just going to join a power series level-wise throughout the cosimplicial object. But that trivialization cannot be made compatible throughout the whole cosimplicial object. And so what one sees is that if you make eta L of t equal to t, then eta R of t will have a sort of interesting formula. It'll be t plus b1 t squared plus dot, 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 for those who know what that means. So that's a formula from Ravenel's Green Book that you can just read off. Some people might be familiar with. But it's still a little bit hard to describe totally in formulas what this is. But to convince you that we've pinned down an algebraic description of it, let me tell you what stack this represents. So the associated stack looks like, or I say classifies, so just like before, we have our formal group, but now we have this t variable, and the t variable can be thought of as a map from the point to G hat. It's a section of the formal group. So just mu star adjoin T would classify the formal group with a section together with a coordinate. So we have the formal group in the section. And we're still going to have our locally trivial metric 2 cocycle, which I might call G. And we'll call this section S. And the last thing we have, which is a new piece of structure, is we can take this canonical line bundle eta of minus 0, things that vanish at 0. And instead of a trivialization of that, which would be a coordinate, what we have instead is an identification of that with g of s comma blank. So the section is some map from a point into g hat. And if I pre-compose my symmetric 2 cocycle with that section in either variable, because it's symmetric, it doesn't matter what variable I use, I just get a map from g hat to bgm, just by pre-composition. It doesn't matter which variable I do it in. And so somehow there are two line bundles in the picture, and one demands an isomorphism between them. This isomorphism is also required to be locally trivializable. So as a result of that, I would say that this is kind of an interesting picture where you can see this non-equivariant coordinate, a very familiar structure on a formal group, being deformed into some relationship between two line bundles, neither of which is zero. This is related to the fact that when you take the totalization, THH of mu HS1 is not in mu algebra. So we shouldn't expect to see a coordinate. And indeed, we don't see a coordinate, but we see something that kind of plays a role of a deformed coordinate. And the fact that you see something kind of close to a coordinate is why the Hopf algebroid seems to have a substantially easier answer than, say, the homotopy groups of the sphere or something like that. Since we're essentially out of time, I will skip talking about how to think about these endomorphisms after P completion at each P. I would love to know, for example, whether this Hopf algebroid, which gives you a spectral sequence computing the homotopy fixed points of THH of mu, has a collapsing spectral sequence. So I'd love to know whether, maybe I'll just end with this explicit question. Does the spectral sequence associated to this Hopf algebroid converging to a star of THH of mu HS1 generate at the E2 page. In principle, computing this E2 page is now an algebraic problem. I will stop there. Thanks.